In current Industry 5.0 human-robot interaction, a stubborn bottleneck exists at the architectural level. Standard engineering practice treats perception, intention inference, and physical control as entirely disjointed, decoupled modules. This modular decoupling guarantees reactive rigidity. The perception module finishes its job, passes the data to the inference module, and the control system sits idle, waiting for the human to finish their action before calculating its own response. To achieve this kind of fluid, continuous collaboration, we have to bridge those modules. The mechanism required to do that is explicit probabilistic linkage. True anticipation means the robot cannot just predict the what, the human's end goal. It must simultaneously predict the how, the specific physical kinematic trajectory the human arm will take to get there. Fluency in a shared workspace is a system-level architecture problem. It requires a unified data pipeline rather than the isolated optimization of independent modules. A theoretical framework developed by Escobar Naranjo and colleagues provides a specific solution to this decoupling fallacy. This blueprint builds a pipeline across three macro stages: perception, cognition, and action. Human telemetry flows left to right, forming a probability distribution of the user's intent. This directly shapes an augmented Markov decision process inside the action block to drive reinforcement learning control. Mastering this continuous, explicitly coupled pipeline separates a robot that relies on reactive safeguards from one capable of proactive fluency. Here we see a 3D wireframe mapping 4 specific modalities of telemetry to capture the variability of human behavior. First are the visual and spatial inputs. RGBD cameras track the physical structure of the human's movement, while gaze tracking isolates their visual focus. Next are physical interaction inputs. Wrist force and torque telemetry measured the exact effort applied, captured alongside the robot's joint states. To process these distinct data types without flattening their unique properties, the streams route into a hybrid encoder. Convolutional neural networks analyze the structural, visual, and gaze data to extract spatial features. Simultaneously, long short-term memory networks encode the temporal dynamics and sequential nature of the force and joint states. At this specific stage, there is a limitation. These encoded spatial and temporal features are isolated from one another. Gathering complex multimodal data yields no operational advantage without a mechanism to cross-correlate that spatial context with the temporal physics. To solve that, the outputs from both encoders funnel into a central transformer attention module. Self-attention allows the network to find correlations across the different data streams. It mathematically links a sudden shift in human gaze with a simultaneous spike in wrist torque. Once fused, the network architecture splits the data into 2 distinct output pathways. To optimize the network, researchers apply a composite loss function, forcing the system to solve 2 different mathematical problems at the same time. The first output treats the human's goal as a classification problem, calculating a dynamic probability distribution over possible future intentions. The second output treats the physical motion as a regression problem, mapping a short-horizon physical trajectory. The composite loss function ensures strict kinematic coherence is maintained between the abstract probability of the intention and the physical prediction of the spline curve. The network does not output a single binary guess. Instead, it provides the control system with a fluid, probabilistic landscape of the human's likely actions. This creates a critical engineering question. How does a continuous control policy actually ingest and act upon a landscape of probabilities? Look at this matrix representing the state vector for a Markov decision process. Typically, this vector only holds standard physical variables like positions and velocities. Explicit coupling occurs here. The intention probability distribution is embedded directly into the state vector, creating an augmented MDP. This augmented state bridges cognition and action, serving as the raw material for continuous control. The controller reading that state is a soft actor critic, or SAC, reinforcement learning agent. The SAC agent continuously observes the augmented state matrix to learn and execute a fluid control policy. It utilizes entropy optimization, which balances the exploration of new, alternative actions against the mathematical need to maximize expected rewards. These rewards prioritize synergy, optimize for efficiency, ensure strict safety, and maintain fluency. By explicitly linking the probability distribution into the MDP, the control policy is empowered to act smoothly on uncertainty. It does not have to wait for an absolute classification of the human's task to start moving. The connected perception-cognition-action loop runs continuously. A real-time shift in human telemetry, like a gaze change, instantly updates the intention probability inside the MDP. This shift causes the SAC agent to alter its trajectory, adjusting the physical path without requiring a hard task classification. Thanks to this continuous feedback loop, the robot adapts its motion while the human is still in the middle of their action. This dynamic mid-action adjustment is the direct measurable result of abandoning modular silos and utilizing a coupled probabilistic architecture. The methodological framework outlined by Escobar Naranjo and their team provides a reproducible, mathematically rigorous protocol that is ready for empirical validation. It addresses an urgent need in current human-robot interaction research, moving beyond single-user, isolated autonomy. As robotic hardware matures, closing the gap between academic theory and active industry deployment hinges entirely on frameworks that support collaborative operations. Proactive collaboration increases assembly efficiency while mitigating the physical friction and safety risks inherent to contested human-robot workspaces. By engineering systems that natively calculate uncertainty, robots become the fluent, anticipatory collaborators required for Industry 5.0.